Hello everyone, this is Shivshankar, Assistant Professor from Government Engineering College, Bikaner, Mechanical Department. Today we will discuss the introduction to refrigeration. In this lecture we will discuss about what is the refrigeration, how it is different from the cooling, unit of refrigeration, Carnot cycle. Reverse Carnot cycle is nothing but the air refrigeration system. Vapor as a refrigerant in reverse Carnot cycle. Okay. Now first, what is the refrigeration? Here the definition: refrigeration is a process that removes heat from space, substance or any system to maintain its temperature below the ambient temperature. In a simple way, refrigeration is nothing but you have to maintain any confined space below the surrounding temperature or the atmospheric temperature. Now, next, how it is different from the cooling. You know what is meant by cooling. Cooling is a process that heat transfer takes place from the higher temperature to the lower temperature. At any point the temperature is flowing from higher to lower, that is meant the cooling, but that is not a refrigeration effect. Refrigeration effect means you have to maintain the temperature below the surrounding temperature. Okay, that is for example, I will explain with the example. Suppose you have kept a cup of tea in a room. Now that cup of tea having the temperature 80 degrees Celsius and the room temperature is 30. Okay, now the heat is transferring from that cup of tea to the room air. That is nothing but the cooling. And when the refrigeration effect occurs, you have to maintain the temperature of tea below the 30 degrees Celsius. That is the air room temperature. That is nothing but the refrigeration. Now next point is what is or how it is give the unit of refrigeration, or how you define the unit of refrigeration. Basically the unit of refrigeration is given as a ton, but here there are two types of ton. One is the TON and another is the TONNE. This TONNE ton is nothing but the metric of ton. Metric of ton. It is a 1000 kg. But this ton TON, this is called the empirical ton. Empirical ton, and this weight is 907.2 kg. 907.2 kg. But for defining of the refrigeration, here we are using this ton. Here not using this ton. Now we will define the 1 ton of refrigeration. 1 ton of refrigeration is nothing but it is the amount of heat that is to be removed from 1 ton of water at 0 degree Celsius is nothing but 32 Fahrenheit in order to convert it into ice at same temperature in 1 day, that is the 24 hours. Okay, means you have kept water at 0 degree Celsius, wait for 24 hours, and that water is converting into the ice at the same temperature. Okay, now how will that is the 1 ton. It is denoted by 1 TR. Okay, now 1 TR is equal to 1 ton of ice into latent heat of ice. Why here I am taking only latent heat? Because there is no change in temperature, only the change in phase. If there is no change in temperature and there is a change in phase, only latent heat occurs. Divided by 24 into 60. That is, you will get this into the kilojoule per minute. Now 1 ton of ice, that is 1 ton, here we are using this ton, that is the empirical ton, 907.2 into latent heat of ice, you know that 335 kilojoule per kg divided by 24 into 60. If you do this calculation, you will get the 211.05 kilojoule per minute. Means 1 TR, here you will get the 211.05 kilojoule per minute. If you convert this into kilojoule per second divided by 60, you will get the answer 3.517 kilojoule per second. That is nothing but the 3.517 kilowatt. Means here we are using the relation 1 TR equal to the 3.5 kilowatt. That is the 1 ton of refrigeration is nothing but the 3.5 kilowatt. It means that for converting water into the ice, you have to extract the heat 3.5 kilowatt. That is 1 ton of water you are converting into 1 ton of ice, you have to extract the heat, that is the 3.5 kilowatt. Okay, next we will discuss the Carnot cycle, because the Carnot cycle is the ideal cycle or imaginary cycle. Okay, here the Carnot cycle is used for the comparison of other cycles, because of the efficiency of the Carnot cycle is maximum. You have learned the Carnot cycle in thermodynamics also. This is simply a recapitulation of the your study. Okay, now you know that I will not go in details, but just I am explaining the PV and the TS diagram of the Carnot cycle. You know that the Carnot cycle having the 4 process. Okay, 2 is the reversible adiabatic process and the 2 is the isothermal process. Reversible adiabatic process is nothing but the isentropic process. Now here we will see the PV diagram. From 1 to 2 process, that is the reversible adiabatic compression. Reversible adiabatic compression process, that is the isentropic compression. Now the 2 to 3 process. The 2 to 3 process is the isothermal expansion, that is nothing but the heat addition. 3 to 4 process, that is the reversible adiabatic expansion. Here the work is to be done. And the 4 to 1 is the isothermal compression, that is the heat rejection. That is 1 to 2 process isentropic, that means there is no heat flow, that is Q is 0. Here also isentropic process, the Q is 0. Okay, now here showing the TS diagram. Here the TS diagram, that is 1 to 2, the constant enthalpy isentropic process. 2 to 3, that is heat addition QH at constant temperature isothermal. Here the work has to be done from this 3 to 4, that is the isentropy expansion, and 4 to 1, that is the isothermal compression, that is the heat rejection. The temperature T2 equal to T3, that is it is indicated by TH. This is here the temperature T1 equal to T4 because of the isothermal process, that is indicated by TL. Okay, now for calculation of the efficiency, here in Carnot cycle we are here for calculation of efficiency we are discussing one parameter, that is the COP, that is coefficient of performance. You know the definition of COP because you have learned in the thermodynamics, that is the RE, refrigeration effect upon the work done, or cooling effect upon the work done, that is QL upon the W. Okay, that is how you calculate the QL. How we calculate the QL? Because QL here in the process from 4 to 1. From the definition of the entropy, we know that definition of entropy, that is the Ts equal to dq upon T. Means Q equal to ds into T. That is the TL, change in entropy. That is change in entropy S4 minus S1. Okay. Now how will calculate the work done? Work done, that is W. From the first law, if you apply the first law for this system, that is W equal to QH minus QL. Because we know that from the first law, addition of work done equal to the addition of the heat transfer. Okay. Now here for calculation of heat transfer, here we will extend this. This is A, B. We know that the work done is nothing but the area under TS diagram. Okay, means area of this rectangle 1, 2, 3, 4. Now how we calculate this area? First we will calculate the total area. Area A23B. Okay, how we calculate area? That is this TH into S3 minus S2 or S4 minus S1. You can write anything, because S3 equal to S4 or S2 equal to S1, because this length is nothing but this entropy difference, and this length is nothing but the temperature, that is the TH. Now area of A14B, that is A14B, this rectangle. Here this is TL into S4 minus S1. Okay. Now the area of this rectangle 1, 2, 3, 4 will get area of A23B minus area of A14B, that is equal to TH S3 minus S2 minus TL S4 minus S1. Okay. Now here we know that the S3 equal to S4 and S2 equal to S1. That is means TH minus TL into S4 minus S1. Okay. Now from this QL equal to TL, put the value in this equation. COP equal to TL into S4 minus S1 upon TH minus TL into S4 minus S1. That is equal to TL upon TH minus TL. That is the COP of the coefficient of performance of the Carnot cycle. Okay. Now here we will discuss the reverse Carnot cycle. Reverse Carnot cycle. Reverse Carnot cycle. Reverse Carnot cycle is nothing but you have to reverse these processes. Means here the heat addition and here the heat rejection. That is the refrigeration. Reverse Carnot cycle is nothing but the refrigeration, because here heat is adding at the lower temperature. Okay. Now means 1 to 4 process is the isothermal expansion. Then this 4 to 3 process is the isentropic compression. Then 3 to 2 process is nothing but the isothermal compression, and then 2 to 1 process is nothing but that is the isentropic expansion. Here I am showing this diagram. Okay. Here I am also changing the notation, that is 1 to 2. Here the heat adding, that is the isothermal expansion 2 to 3, that is the isentropic compression 3 to 4. 3 to 4 is nothing but this is TS diagram. 3 to 4 is nothing but the isentropic compression, sorry, it's isothermal compression, that is heat is release, and 4 to 1 is the expansion. Okay, this is nothing but the air refrigeration system. In detail we will see this is in next lecture, air refrigeration system. Okay, if we use the vapor as a refrigerant, what will happen? Vapor as a refrigerant. For this system, the refrigeration works in between the change of phase state, because we know that this is shown here that this change of state phase, that is this, because we know that at constant temperature there is a condensation and boiling. Okay, condensation and boiling, that is 1 2 3 4 process. Here the condensation takes place at constant temperature, this is TS diagram. Here the condensation takes place at constant temperature, here the boiling takes place, it is at the constant temperature also. Okay, thank you.